Welcome. In this video, we are going to take a look at more implicit differentiation, and we're going to take the next step into considering how to find tangent line equations at a given point on the curve. So we have the first example here as x squared minus 3xy plus 7y equals 5, and we would like to find the equation of the tangent line at that given point 2, 1. So let's consider first what we need to have for a tangent line. The first thing we might want to consider is, well, what is the tangent line slope and how would we find it? So for our tangent line slope, well, another way to consider that is going to be the derivative of our function evaluated at 2, 1. So in this case, what we're going to think about as our slope is the derivative dy dx. And we'll evaluate that at the point 2, 1. That's what we're going to be looking for when we find our slope. So instead of having the tangent line slope be a derivative at a single value of x, we now have to define this point as a x, y value. So let's go ahead and take our derivative first implicitly. We'll evaluate at our point, and then we'll continue with the construction of the tangent line. So first, let's go for that derivative. We want to take the derivative with respect to x of both sides. So let's go ahead and consider that. We have the derivative with respect to x of the left side, and we have the derivative with respect of the right side. ddx. So jumping in, we will have the derivative of x squared becomes just a 2x. Then we come across the second term here, which is a product. So we'll have a 3x term and a y term here. And to just make this a little bit easier, we'll just pull this negative sign out, and we're going to do the product rule right in here. That first term, 3x, let's go ahead and consider first. We're going to have the derivative of 3x is going to be 3 times the second term, which is the y. And then we'll add to that the 3x term. And then the derivative of y, we would call again dy dx. So we'll take that dy dx last. So there's our product rule sitting there. And then we want to take the derivative of 7y as well, and we could call that plus just 7 times the derivative of y, which is dy dx one more time. If we look at the right side, we just have a constant term here, which is 5. The derivative of just a constant with respect to x is going to be 0. So we'll set that to 0 when we take the derivative. Looks like we can go ahead and distribute a negative sign here. We have 2 derivative terms and 2 non-derivative terms to collect. So let's write that all in one statement. We have 2x minus 3y plus, minus, because we're going to distribute that negative sign both times, 3x dy dx, and then plus 7 dy dx, all equal to our 0. Okay, so we have a good looking equation now. We have 2 derivative terms on the left, and we also have those 2 non-derivative terms. So let's go ahead and move those over to the right. We'll subtract 2x and add 3y to both sides. And those will cancel on the left, just leave us with our derivative terms on the right. Looking good for us. So one way we can simplify this down a little bit again is we have 2 derivative terms dy dx. We'll go ahead and collect those now. So we have dy dx factored away. We'll have a negative 3x and a plus 7. Doesn't matter which order you write those in, but we'll just write it as that for right now. And then we have another term here. We'll have negative 2x plus 3y. When we put these together for the derivative, we could just divide both sides by that linear function, divide by negative 3x plus 7, and that will give us our dy dx derivative. So this gives us our general derivative. To find that tangent line equation, though, we would like to apply the point 2, 1 to that derivative. So let's go ahead and follow that up. We're going to want to evaluate my dy dx, which is equal to negative 2x plus 3y, negative 3x plus 7. We want to evaluate this at the point x equals 2 and y equals 1. So let's go ahead and evaluate here. We have negative 2 times the x, which is also 2, plus we'll have 3 times the y, which is 1, divided by negative 3 times x, which is 2, and then plus 7, which is just going to be a constant. So this will give us our tangent line slope. Looking at the numerator, looks like we'll have a sum there of negative 4 plus 3, negative 1. And looks like we'll also have a positive 1. We'll have negative 6 and 7, positive 1. So our slope here is just going to be a negative 1. So that's our tangent slope. So when I consider the tangent line equation, we can kind of set up this with a point slope form to begin. We had y minus y1 equals our slope, which is going to be our tangent slope. We'll call that m, x minus x1. So that's our point slope form for a line. We'll take our tangent slope, which is negative 1, and we'll take our point 2, 1 as our x1 and y1. So we would list this out as y minus y1, which is 1, equals negative 1 times, we have x minus x1, which is 2. We can distribute the negative 1 and then add 1 to both sides to find our final results in slope-intercept form. And we get y is equal to negative x plus 3 as the intercept value. And that will become our tangent line equation. Now, it might be nice here to consider a visualization for this. And the best way I've found to consider these implicit equations is to take a look at these in Desmos and just see how they line up to our tangent line equation, just to check our work here and see if we've done a good job. So let's go ahead over to Desmos. I'm going to show you guys how this function matches up, or at least this curve matches up to our tangent line equation at 2, 1. So we have our curve. That's the original curve. Let's just take a look at what that looks like. It's going to have kind of these V shapes to the side. And I'm specifically interested in the point 2, 1 that's on the graph right here. We'll notice that if we put our tangent line equation that we found on the graph, I think that does really well in representing our tangent line equation. That's the only point we cross, and we glance off of that point at 2, 1. So that's looking pretty good visually for the tangent line equation for that implicit function. So that matches up pretty well visually for the algebra that we've done. We'll take a look at the graphs for the next few problems as well as we work through them. Let's go ahead and jump into a second example with the tangent line equation. If you take a look at this second one, x squared plus 5y squared plus 45, this is really going to be a shape of an oval, and we'll see that later on. This is going to be some oval shape. And then we're going to consider this, so the shape of this would look probably a little bit like this. Still going to be centered at the origin, but just consider kind of an oval shape. And we're going to be interested in really the point 5, 2, which is kind of up in the first. If this is the origin, 5, 2 might be somewhere over here, and our tangent line might possibly look at something like this that has some negative or decreasing slope here. So we'll look at the actual graph soon, but that might be something to think about. We probably should have, based on that analysis there, a negative slope here. So we'll try to check that when we go to the actual graph as well, see if that lines up. So we first want to take our implicit derivative. We'll try to find our tangent slope and then go from there. So derivative with respect to x of both sides. We'll have only a couple terms to work on this one. So this would become just 2x plus, we'll have 2 brought down is going to give us a 10y, and then we do want a dy dx term here, derivative of the y function with respect to x. And then on the right side of this equation, again, we have a constant 45, which is going to be a 0 when I take its derivative. So let's walk this through for the dy dx term. We can subtract the 2x on both sides. And then we could go ahead and divide both sides by the 10y. And it looks like our dy dx term, we can simplify here, is still dependent on x and y. And if we reduce this, we'll have negative x over 5y for our general derivative dy dx. So looking at this, we would like to, again, evaluate this at the given point. They give us that point 5, 2. So let's go ahead and evaluate x equals 5, y equals 2. So this would give us a negative 5 divided by 5 times 2, which gives us really a 1/2, or a negative 1/2 in this case here, negative 1/2. So there's our tangent line slope again, negative 1/2. And if we'd like to start with that point slope form, we could rewrite that as the slope intercept form. That's the likely form that you'll want to represent your equations. So again, we have y minus y1, y minus y1, and then my slope times x minus x1. We know our slope and we have our point, so we'll have y minus 2 equals negative 1/2, and then x minus my 5. Again, we can look to distribute first to get negative 1/2 x. And then we'll have plus 5/2. We can add 2 on both sides. And when we add 2, the equivalent to adding 2 here would be really adding 4 over 2. So we'll consider that as really a 4 over 2. So when I consider that, we'll have a final result here. We still have the slope of negative 1/2. And if I have 5/2 and 4/2, we could write that really as a fraction here as 9/2 if we'd like. You could also write this as a decimal. Y is equal to negative 0.5x, and that would be 4.5. Either way, that works. Be nice to be consistent there with either a decimal result or the fraction. So there's our tangent line equation. Again, let's go ahead and maybe take a look at the graph and just see how we did based on this equation of really an oval equation at the point 5, 2. We'll go over and do a flyover here. We have our original function coming up here, and we're going to consider the point 5, 2. So again, it's a little oval here that's elongated along the horizontal x-axis. And we have the point 5, 2 that lies on the top right of that oval. And if we look at the function that we found, or the linear function, that looks pretty good for that tangent line curve. So if we kind of zoomed into that, we will only really hit that point at that singular point if we get really, really close. And we'll have that correct tangent line equation. That's looking pretty good. So again, we're not necessarily using Desmos to solve this. We solved it on our own on paper, but this is maybe a good tool as you're doing their homework to just consider graphing it, visualizing it for yourself to see where you were at for your solution. We have one more to consider together before we close out. This one involves a natural log function. So let's go ahead and jump into part C together. So we have the natural log of y plus 3x equals 7, and we're considering the point 2, e. Remember, e is a constant value here, so we'll want to treat that as a constant. So let's go ahead and take the derivative with respect to x of both sides again, and we'll walk through the tangent line process. So we have the derivative with respect to x, and then the derivative with respect to x. So the derivative with respect to x of the natural log of y, well, usually natural log of y will have the 1 over x derivative, or the 1 over the argument, so that would be the 1 over y function here. Since this is a function of y, we want to take the derivative with respect to x of the y variable. That would be, again, dy dx. So we have 1 over y times dy dx plus the derivative of 3x just becomes 3. We're taking the derivative with respect to x, so there's nothing to work with the chain rule. And then we'd have another constant 7, which becomes a 0 as its derivative. So this derivative actually happens to only be dependent on y. If we rearrange these terms a little bit, we'll subtract 3 on both sides. We'll have just a 1 over y dy dx is equal to negative 3, and then I can multiply both sides of the equation by y. So if I multiply by y, we can go ahead and cancel those values out to just get dy dx is equal to negative 3y. Again, this is just dependent on y, so all we need is the value of e here to consider the tangent line slope. So if I evaluate this at 2 comma e, the y is the only one taking part with this, so that would just be negative 3e, and we'll just leave that as the expression with e. We don't want to go to a decimal necessarily. We want the exact solution here, so we'll leave it as negative 3e for that result. That's my slope. And now we can use that slope and our point to consider that tangent line. So let's put it together. We have y minus y1, my slope, x minus x1. So this is our payoff. We'll have my y term here is e again. So we'll subtract e equals my slope, negative 3e, and then we'll have x minus x1, which is the 2. We'll go ahead and distribute the slope to get negative 3e times x, and then plus, when we distribute the two double negatives here, we'll get a plus 6e. And then to finish this up, we'll add the factor of e to both sides. Those will actually be like terms there that we can add. And our final result here for the tangent line will have y equals negative 3e times x plus 6 and 1e becomes 7e for the constant term. So keeping it in terms of e is the best way to go here to have that exact result. So we have the slope of negative 3e, intercept value of 7e. Again, this would be a good one to just take a look, see how we did on our graph. So we'll look at the equation and then the tangent line as well at the point 2 comma e. Let's go over to Desmos one more time to consider that result. And we'll scroll down and go ahead and grab that equation. We have our point. Looks like we should have a negative slope again, which I think matches our equation. Let's see how we did. That's looking pretty darn good with the green tangent line and our purple function at the point 2 comma e. So that's just a visualization of the implicit equation and our tangent line to that. So I hope this was helpful walking through implicit differentiation and tangent line equations. We're going to take a look at some related rates in our next video. Hope you guys take a look at that one. Thanks for watching, and I'll see you in the next one.